Hi, Taylor here. Let's get started on question 14 of the Spring 2019 MAS 1 exam. You are given the following simulation process to generate random variable x using the rejection method. X has a beta distribution f of x with parameters a equal 2, b equal 10, and theta equal 1, and is concentrated on the interval 0 to 1. The rejection method uses g of x equals 1 for x between 0 and 1. The rejection procedure is as follows. Step 1. Generate independent random numbers y and u which are both uniform on 0, 1. Step 2. If u is less than or equal to f of y over c times g of y, stop and set x equal to y. Otherwise, return to step 1. Calculate the minimum possible value for c. Alright, let's see. So for this question, things you need to know are, one, just taking derivatives, so specifically using the product rule is going to be used in this. And then second, what the rejection method for simulation is, or I also have specifically here that the function is f of x over g of x and what f and g correspond to. So I feel like with this question, we're actually really lucky with how detailed they got with all the notation and walking you through the algorithm itself. So I would consider this a really generous problem, a well-written problem, and I wouldn't go into the exam assuming that they're going to be this friendly in the future necessarily. So I want to take a step back and really walk through what's going on visually, because I find this a lot more helpful than all the notation. So first off, beta distribution. I have that plugged in here, so this orange curve is our targeted beta distribution we're hoping to simulate from. I then second have our g of x function, which is a uniform, and that's our y as well as our g of x. I feel like it's kind of complicated the way they have that outlined, but really it's y. G of y is just always 1, so it's a uniform from 0 to 1 to 0 to 1 on the y. And then if we were to just multiply that by an arbitrary 5, so we're going to say c equals 5, we see that we have this blue curve that is always greater than or equal to our orange curve. So now if all we know is how to plug x values into our orange PDF and get out the corresponding PDF value, how can we, using only that and the ability to simulate from a random uniform, simulate points that follow this orange distribution? And the way you can do that is by, okay, well, I'm going to first off just simulate a random value in between 0 and 1, and that's going from left to right. And then I need to decide, okay, well, I did that, but now if I just accept all of these simulated points, it's just going to be a uniform distribution. It's not going to follow that orange curve. So what I need to do as a second step is then say, okay, well, what if I strategically reject a certain proportion of the simulated values based off of where it is in terms of its x value? So what I mean by that is if I simulate, let's say, a 0.98, something really far to the right, looking at this orange curve, I can see, well, that should almost never happen. And so I would like to reject that point almost all the time. And so what we can do is simulate a random uniform, so that's going to be 0 to 1, and then multiply by that 0.5. And essentially you just get a random value, and then what you do is say, well, is it in the blue region or the orange region? And if it's in the blue region, I'm going to reject it, and that's denoted by these red colors. But if instead I simulate a point, let's say 0.1, and then I simulate a second point, so let's say in this case here that was a simulated value of close to 0.5 multiplied by 5, and we got something right here. And so since it fell in that orange region, we simulated the x value, and then we simulated a y value between 0 and 5, and since it fell in the orange region, we decided to accept that initial simulated x value. So that's what the algorithm is doing. It's just simulating x's and then y's and comparing it to whether it falls in the blue or orange region. And at the heart of it, that's all the accept reject method is. So now what you might notice is, okay, well, if I want to make this algorithm as efficient as possible, that is, minimize the amount of times I need to reject, what I can do is, instead of using c equals 5, I can use a smaller c value. That's going to move it towards this peak of the orange distribution. And that's going to minimize the amount of times that we actually reject points because there's less blue area. So we're going to work through the math next, but we'll see that the answer ends up being 4.262. The one other thing you can do to make the accept reject simulation method more efficient, and this is not at all related to this problem specifically, but the distribution you simulate x values for does not have to be a uniform distribution. So if you're given a beta distribution that's bounded between 0 and 1, it seems really easy and clean and nice to just use uniform. But let's say you were trying to simulate values from a normal distribution. You couldn't use uniform for that, right? Because you couldn't simulate a value greater than 1 or less than 0. So you need a blue curve that also has the same bounds, negative infinity to positive infinity. So the way that corresponds to this problem is if instead of uniform we had a curve still bounded between 0 and 1, but more closely aligns to this orange distribution, that would also help you in minimizing the blue area. So that's just to say this g of x function does not necessarily have to be a uniform distribution. So now to jump into the actual calculations here. So first off, just going into the formula sheet, pulling the PDF for a beta distribution, and then plugging in those values. Alpha is 2, beta is 10, and theta equals 1 gets us this mess on the left here. And that simplifies to 110x times 1 minus x to the power of 9. And then again, g of x is just equal to 1. So now what we want to do is maximize their ratio. And the reason for that is we're trying to decide what is the multiplier we need to make it such that the blue curve is always greater than the orange curve. And so since g of x is just 1, it's just trying to find the maximum value at the beta. And so this is where we take the application of the product rule. So that's going to be the derivative of the left multiplied by the right, and then the derivative of the right multiplied by the left. And that's how we get this long equation here. Next, scrolling down, so that's just setting it equal to 0, because again we're trying to find the maximum. Technically you would want to then take the second derivative and see if it's a minimum, but since we know there's only one peak, we're just going to set it equal to 0, and what we get we're comfortable in knowing that is the correct answer. So setting it equal to 0, dividing both sides by 110, because that's a common factor, as well as 1 minus x to the power of 8. So all we're left with is 1 minus x on the left side, and then 9x on the right side. And then finally we can solve that to be x equal 1/10. At this point, this is where I feel like I would get excited and say, oh, the answer is 1/10 and be done, but rereading the question you'd see that it's asking for the smallest value of c. And so for this we're going to do f of that x value 0.1 divided by g of 0.1. And so this is how we're getting that value of 4.262. So our answer for this question is D. Thanks for watching. Please consider subscribing if you find these videos helpful. Have a good one. Bye.